from the
Sorry about that.
sounds good. So, morning everyone. Today we are going to veer off a little bit away from the Bayesian optimization and talk about the variational autoencoders and what type of tasks they allow to solve. So the reason why it is super important is because the autoencoders is the foundation for deep kernel learning, which is essentially the way that allows to extend the Bayesian optimization towards the high dimensional spaces. Variational encoders can be used in many different ways combined with the Gaussian processes. And ultimately, they bring forward some of the key components of the intuition required to use the deep learning in general. So so I've been working with the VIEs basically starting from 2019, sort of in the early COVID times. And the interesting part about using the autoencoders was that they bring a lot of new notions that are absolutely foundational for their use for ML tasks and especially for physics tasks. These notions are usually not a part of the intuition that we develop as physicists or domain experts. So they are, in some sense, absolutely non-obvious. And in some sense, we have to build upon them in order to be able to use the machine learning in general and to be used the Bayesian optimization methods based on the deep kernel learning or simply Bayesian optimization in the latent spaces. So today we are going to look at what are the variational autoencoders and try to build the intuition for the concepts of encoding and decoding, latent distributions, lateral representation, and particularly what is the disentanglement of the representation. I'll show how we can modify the autoencoders to suit the specific physics tasks, to add the invariances like rotational, translational, shear, and so on. These invariances, of course, can be much more complicated. For example, if I want to build a variational autoencoder for the X-ray data, I will build the invariances that are responsible for the change of the unit cell rather than anything else. There are multiple ways how we can extend the concept of the autoencoder towards the semi-supervised, conditional, and joint. And then I will illustrate few real-world examples and illustrate how we can build the encoders, decoders. So there is no need to autoencode. We can encode one property and decode another property. And how we can run the Bayesian optimization in the latent space of the autoencoder. So today we will stick primarily to the PowerPoint presentation. So I uploaded one notebook that talks about the VIEs, but generally this by itself can be considerably more than one lecture. And this, in some sense, would be the foundation for the active learning in the deep kernel. So let's start with the very, very simple introduction of what the autoencoder is. So for the time being, it's not a variational autoencoder. This is just an autoencoder. So, and I'm showing the example of how we can apply it to the MNIST dataset, so the handwritten digits. So imagine that our input data to the autoencoder are either images or spectra or any other dataset. So the first thing that autoencoder does, it passes this data through the convolutional or just a fully connected layer funnel until the data is compressed to the small number of latent variables or a small number of variables, like a bottleneck in the neural network structure. Then what it does, it takes these latent variables and tries to deconvolute it back into the original data dimensionality. So the way that the conventional autoencoder is trained, it basically tries to take the image, compress it to the small number of the latent variable, and then learn how to decode it back to the original image. And our loss function, in this case, would be simply the reconstruction loss between the image that goes in and the image that got reconstructed. So at the first glance, autoencoder is a very weird type of the neural network which essentially all it does, it tries to reconstruct the data from itself. So the question is, why is it necessary, and what do we gain as the result? So the first thing that we gain as the result is the fact that each image or each object in our input data set start to be represented as the small number of the latent variables. So for example, for the MNIST image, so this is 28 by 28 pixel size. So if we compress them to the two-dimensional latent spaces, so two dimensions are very easy to visualize, then each image in the MNIST dataset becomes a point in this latent space of the autoencoder. So this is just the case when we have two latent variables. So the first thing that you are going to see that if we have 50,000 points, 50,000 images from the MNIST dataset, their distribution in the latent space start to have a certain structure. So for example, zeros are sitting in this part of the latent space, sevens are sitting in this part of the latent space, ones are sitting in this part of the latent space. So this representation is called the latent distribution. So if we have some data set, we pass it through the autoencoder, and then we explore the distribution of the latent codes corresponding to each original data set. This becomes a latent distribution. So the key thing about the autoencoders is that they're generative models. And what that means is that, in principle, we can take a point, each point in the latent distribution, send it to the decoder, and reconstruct our original image, or something close to that, sort of minus the reconstruction loss. However, we can also take a point anywhere else in the latent space, and we can decode the image from this latent point. Notice a key thing, that we did not have the example of the image that corresponds, for example, to the point -1, -2. But we can still decode, and we can see how this image from this point would look like. So this is very important aspect that makes autoencoder a generative model. So by now, all of you are familiar with the things like ChatGPT and so on and so forth. So they, in some sense, use fundamental idea is exactly the same, that you can generate the new entities that come from the same distribution. So you can ask a question, where does the information required to produce the image from the latent codes come from? Very simple. It is the information which is reflected in the weights of the decoder. So it's not coming out of nowhere. It's actually this part, this trained network. So the second key component of the autoencoders is so-called latent representation. So what the latent representation is that we take our latent space, we sample it by the rectangular grids. So we basically divide it in the kind of square segments, and then we decode an image from each point of this latent grid. So in this case, if we do it for two-dimensional case, we get a representation like this one. So each small image here corresponds to the specific latent vector. So notice very interesting thing, that all of a sudden, if you look at this figure overall, you start to realize that it has some sense. So for example, here we have zeros. And it makes sense because this part of the latent space was occupied by zeros. And if we reconstruct things from there, we do see the zeros. This part is populated by ones. This part is populated by, you can recognize sevens, nines, and so on and so forth. This part of the latent space is populated by very weird symbols, which are kind of look like they're in Klingon. In some sense, that makes perfect sense, because if you see here, we see that on the one side there are zeros, on the other hand is ones. So if we try to decode from this part of the latent space, we kind of get some interpolation between the 0 and 1. And that doesn't look particularly convincing. In other cases, say between 7 and 9, we can actually interpolate reasonably well. So we have the figures which are, you never sure where it is 7, where it is 9. What's very interesting is that if you mean, by now, we really don't work that much with the handwritten text anymore. But you remember that when handwriting was a thing, some people have a good handwriting, and then we can separate zeros and ones very well. Some people have poor handwriting, and sometimes it's difficult to recognize where the person wrote 9 or 7. So that actually, this mixing kind of represents how the human operation also works. Another thing that you will notice is that if you look at this part where the zeros are, you can see that there is some systematic changes from how the zeros look like from this point to this point, or from this point to this point. So it's not like they change rapidly. There is clear some ordering here, and we'll talk about it in a few seconds. Now, how important are autoencoders? So this is the example of the Google Scholar page from Jeff Hinton. So probably one of the 3 most famous people in the field of the artificial intelligence. So notice that he invented autoencoders in 2006, so less than 20 years ago. By now, this paper is published is cited by more than 20,000 times. So that's actually a fairly old one. So the autoencoders are really, really important. So what else can be they used for? So the typical way we can use autoencoders is denoising. So the reason why autoencoder work for denoising is that we take the data, we compress it to this needle eye of the latent variable, and when we do that, all the spurious parts of the data get rejected. So there are only a small number of entities in our encoded in our autoencoder. Noises can be very different. So the noises get rejected by the autoencoder latent layer. So the way we train these denoising autoencoders is by the pairs of high noise and low noise images. And then the way we apply it, we provide the new high noise images. So one thing to be very careful about, so there is no free lunch in machine learning, and to the best of my knowledge, no free lunch anywhere. So this will work if and only if the images come from the same distribution. So if you try to train the autoencoders of the pairs of the high noise and low noise images for NIST dataset, it works wonderful. So this is ground truth. These are noisy images. These are reconstructed images from the high noise images. You see that they have worked exceptionally well. So the autoencoder was able to recognize 3 here compared to the ground truth. I would not be able to see it myself. It's kind of exceptionally good. However, if I try to denoise the Chinese characters as opposed to the classical Arabic digits, I will still get Arabic digits. So one have to be super careful using the autoencoders for denoising the data if the data was out of the distribution. So if you train your autoencoder using certain X-ray data sets, and then you think that you can use it to denoise the results of the fast X-ray measurements, that may work, but if your training set can contain the feature from a certain secondary phase, then this phase will be showing up at the denoised images at the same time. So the best advice I can give about using the variational autoencoders for decoding is that use them as the way to identify potentially interesting and meaningful data, but then always go to the classical data sets for which we know how to handle errors and the kind of creation of the false positives. Otherwise, it's a way to do a lot of really bad science. So another way we can use the autoencoders is for the color restoration. So imagine that we train them on the pairs of the grayscale and color images. We apply them on the new grayscale images coming from the same distribution. So this is the example. So this is a test color images. So the autoencoder have never seen them. We make them grayscale and use them as an input to the autoencoder. And then the output is the colorized. So this is a very simple example where you can see this out of distribution effect. So notice that here we have a ship which is in the green sea. So it's just an unusual state of the sea where it is the water looks green. Notice that the reconstruction of the ship is actually in the blue sea because the vast majority of the training images have the sea being blue rather than green. So, the same thing will apply to all the other images here. So when we reconstruct, we get the most probable colors, but we don't have the true color. So that's a very important to be aware about this type of limitation of autoencoders. Now, the next related concept is the variational autoencoder. So variational autoencoder is even newer comer to the world of the machine learning. So they were created in 2014. So barely they're barely 10 years old by now. So the paper by Kingma and Max Welling has introduced the variational autoencoders. By now is something like 30,000 citations. So it's a big thing. The difference between autoencoders and variational autoencoders is in the way they sample the latent space. So the autoencoder just does the rigid deconvolution. Variational autoencoder uses the reparameterization trick, so it samples latent distribution rather than rigidly deconvolve it. So for the first time you are using them, it is not that important. It becomes important if you start to use the uncertainties as well as the predictions, but to the best of my knowledge, there is no published work where they have been used for something useful. So for the time being, assume that they can be used for the same task as autoencoders. Now, the key aspect of the variational autoencoders is that they start to exhibit a fundamentally new behavior, which is called the disentanglement of the representation. So let me first illustrate how the VAE trains. So this is the example of how the VAE trains for the MNIST data sets. So how the latent space evolves with the training. So how it learns to identify the figures and how the latent distributions evolve with the training. Now, what is disentanglement of the representations? So imagine that now I make my autoencoder a little bit more complex in a sense that I not simply encode the MNIST dataset, but I encode it jointly with the class. So in this case, I generate a latent space for each digit, so 0, 1, and so on and so forth. And instead of having one latent space where all digits are encoded, I have 10 latent spaces, one for each digit. So notice a very interesting thing that happened in this case. So look at the latent space for sixes. All sixes are kind of oriented vertically and chubby on the left. And if I move from left to right, they become progressively thinner. At the same time, if I move from top to bottom, they start to tilt from being vertical to being tilted to the right. And now if you look at the sevens, eights, and nines, you can see that they behave in exactly the same sense. So somehow the autoencoder, variational autoencoder, learned to separate the nonlinear factors of variability in this human handwriting. And this nonlinear factor variability, if in this case is the tilt, so we typically, when we write our digits kind of have different tilts. And the second factor of variability is the width of the letter. Some people kind of write in this short angular script. Some people tend to write very broad digits. So this, obviously, this is not a pure separation. So you can see that for sevens, additional factor of variability is the presence of the horizontal line here. So some people just write 7 like this. Some people write sevens like this. So this also become a factor of variability. But by far and large, this representation of the data in such a way that the nonlinear factors of variability become visible and clearly separated, this is the most unique and the amazing part of the VAEs when they applied for computer science problem or the physical problems. That was the reason why I was always interested in them, because in some sense, when we try to explore the physics of complex system, we look for simplicity. So something like order parameter representations and condensed matter physics, characteristic behaviors, and so on and so forth. VAEs are absolutely amazing for discovery of this type of behaviors. They just work. So interesting thing is that, to the best of my knowledge, there is still no theory or even rigorous definition behind the disentanglement of representations. So that's a behavior that happens. It's very easy to illustrate, and which is mathematically not defined, at least at this point. So it's actually super cool. Now, so let's assume that we want to apply the, let's make explore how the autoencoders can be used for the real world requirements. And let's start with the, and as the way to build the intuition about how the autoencoders behave and operate for the real world systems. So MNIST data set is a little bit complicated. It has 10 digits and kind of too many things to keep an eye on. So let's assume that we build the simplified data set that has 4 hands of cards. So the clubs, pikes, hearts, and diamonds. And let's see how the autoencoders are going to behave if we introduce the disorder in those data sets. So in this case, we try to explore the card behavior in the presence of the rotational and translational disorder. So rotational means that we have a hand and we kind of rotate it a little bit. And translation means that we shift it around within the image plane. And we also can add shear, meaning that we introduce effectively strain to these images. So let's say that we introduce the several data sets when there is a low rotational disorder, low shear disorder. So they look almost ideal. We have low rotational and high shear disorder, and then high rotational, low shear, high rotational, and high shear. So you can see that the representation of the images from these data sets are kind of represent the strength of the disorder. So let's see how the VA will work on those data sets. So let's start with the first example when we have a low rotation and low shear. So this is our data set. We just get the arbitrary samples. So there is no logic from their arrangement. These are just randomly drawn examples. And this is what is going to happen if we have the latent representation. So now we encoded the cards in the latent space, and we decoded it from the lattice. So in this case, we have the axis and the axis matter. So in this case, you can see that the latent space is now divided between the diamonds, pikes, clubs, and hearts. Notice that the reconstruction is almost perfect. So we can see some examples when they are kind of mixed, but not too many. And now we start to look at how the structure of the latent distribution and the disentanglement of latent representation shows up. So see what happens in this case. So this is the latent distribution. We took our card data set and encoded it down to the 2 latent variables, and we now visualize the distribution. Notice that all 4 suits are clearly separated. So I don't remember which one is which, but you can see that all the original objects are sitting on the same, on its own one-dimensional manifold. And now notice a very interesting thing, that in this case, we have access to the ground truth data, meaning that for each card, we have the access to the shear and angle. So once we have the access to the ground truth data, we can see how the ground truth factors of variability are distributed in the latent space. And here the most amazing things happen. Notice that the angles are changing uniformly along each manifold. So somehow the angle changes is always minus 10 here and 10 here. And for each of the cards, it goes like this, except for this one where it actually starts from 10 and then goes to minus 10. So if you look at this picture, you somehow see that this direction in the latent space becomes aligned with the angle. this direction in the latent space, which is perpendicular to it, becomes aligned with the suit. So obviously the suit is a discrete variable, so we have only 4 manifold, but you can see that this change from the lower left corner to the top up corner, and this one changes in the perpendicular direction. So that's what the disentanglement of the variables looks like. And that immediately tells you how you can use this in the real world problem. So imagine that I have cards where I don't know the angles. So I don't know the angles, but I know that my latent variable have encoded some factor of variability, and I can actually assign it based on the latent variable. This is a super powerful tool to explore the real world data. Notice another interesting thing, that we actually start to see that the shear, which is our third factor of variability, in addition to suit and angle, also changes. It kind of changes weekly, so you can barely see this gradient, but you can also see that shear locally changes orthogonally to the angle. It didn't disentangle very well, and it makes sense because our embedding space is two-dimensional, and we have 3 factors of variability. So suit and angle are the strong factors of variability. They take over the latent space, and the shear tries to get disentangled as much as it can given the space constraint. So see what happens if we now introduce the second data set where we have a low rotation but high shear disorder. So in this case, the behavior of the latent distribution is different. So we still got the separate clusters responding for the suits. So suit is still the major factor of variability. You can see that if we have we would probably not be able to classify based on this data set. So you can take this and use the DB scan in order to separate different hands, but that will require quite a lot of data to work. But you can see that, for example, the manifold for this card, for the suit 1, got split by the manifold by this one. So you try to take a system with a 3-dimensional variability and project it in the best way on the 2-dimensional data set. You get some useful representation, but of course, here you will need to kind of experiment to make it work in the optimal way. Look how the disentanglement for the shear and angle look like. So in this case, shear and angle become comparable in terms of how strong disorder it is. So they are not separated clearly, but you can see that locally shear and angle still are orthogonal. So the angle changes like this and the shear changes like this. So this is again, this is what makes the VAE a unique tool for analysis of the data. So what happens if we introduce the disorder, increase the disorder? So let's say we have high rotation and low shear. So notice what happens in this case. The manifolds become essentially like a spaghetti, so the whole space is spaghettified. So the shear is not disentangled very well. The angles change systematically across the data set, so the colors are relatively clear, but there is a clear variation from the large rotation angles here and small rotations here, but it's still clearly not a very good disentanglement. Then finally, see what happens if we have the high rotation and high shear disorder. So in this case, you can immediately see that the VAE did not work very well. So you can see that the latent representations are fairly fairly smeared out. That tells us that our reconstruction loss is actually pretty high. And the latent distributions, okay, in this case, we can clearly see internal structure, but you see that we have 3 strong factors of variation, suit, shear, and angle. We try to represent it in the 2-dimensional spaces, and they kind of fight each other. So they still locally disentangle. So you can see that there are big groups of the points corresponding to the different suits, so they're well separated. Locally, the shear and angle will still be orthogonal, but overall, we can make sense out of these distributions only if we have access to the ground truth. That being said, for something like this, or for something like this, or for something like this, we can use those for discovery even if the ground truth is not available, simply because the way that data is organized clearly suggests that there are 4 groups of data. And if we explore the variation of the properties of the object reconstructed from different parts of these manifolds, we would be able to identify what they are and what are the factors of variation. So practically, I've shown this as an example for the model data sets, but trust me, this type of tools work for analysis of the imaging data incredibly well, and then they can be connected to the physics and structure of the material in a very, very informative ways. Now, the important thing is that classical autoencoders tries to treat the angle as the independent variable. So what we can do is we can take the autoencoder and use the latent space to define the values of some latent variables. And one way to do that is to introduce the invariant autoencoder, for example, rotational VIE. So in this case, we have the usual latent variables, and additionally, the autoencoder tries to learn the rotation angle. So it kind of clearly separates from the other latent variables and assigns the meaning to that. So in this case, the decoding process start to work remarkably better. So for example, if I have a low rotation, lower shear data set, then my latent distributions become essentially dots. So they are very, very well separated in the latent space. In this case, shear start to disentangle. So compare the example of the classical VIE. So in this case, the suits are 1 factor variation. Angle is the 2nd factor variation. Shear tries to disentangle in whatever real space state is available to it. So if I have the rotation invariant VIE, then now I have very clean groups corresponding to the pure suits. Shear is very clearly disentangled in this direction. And I also get an access to the angle. And interesting thing is that if I try to compare the ground truth angle to the decoded angle, they of course come with the offset. There is no way for the autoencoder to know that the native orientation for the diamond is this one and not this one. But you see that the variation is the same. So this changes from minus 0.2 to 0.2, and all of those change from minus 0.2 to 0.2. So we learn the true rotation angle of the object. And it works remarkably well for other scenarios. For example, if we have low rotation and high shear, this is how it looks like. So we still have 4 groups. Our shear changes is disentangled very clearly across the manifold. Angles become a little bit more noisy, but it still works remarkably well. And it works exactly well for the high rotation. So notice what happens in this case, that for high rotation, when we have 180-degree disorder, we have disentanglement of shear. Notice that one of the group of cards got split in 2. I suspect it happened because of the fact that the diamond can be an object like this on an object like this, so they're difficult to separate. And this is respected in the ground truth behavior. So you can see that for one of the suits, the reconstructed angle kind of jumps by 180 degrees. But these behaviors are fairly easy to identify even if we don't have access to the ground truth labels. And what's important that it even works for the very high rotation and high shear behavior. So the manifolds become more complex and they sort of start to crisscross. But nonetheless, it clearly works much better than the original for the simple VIE. So the idea is that adding the known invariances into the VIE approach is actually makes it much more powerful. And this is the basis of the kind of physics learned for the representation learning. So if we take the VIE as the black box algorithm, we take a data and we produce the latent variables out of it. It's super useful, but it's very difficult to explain what it does. So it typically takes quite a lot of time to meditate over the latent representations in order to say that, okay, this latent variable can be interpreted roughly like this behavior. Once we add the invariances like rotational, translational, and scale, then some of our latent variables start to have meaning, which is actually very close to the true ground truth physics for the cases when we know the ground truth. And the second super important thing is that the remaining latent variables become considerably more simple. So the way that we will use the VIE on the real world problem is almost like unpeeling the onion. We start with the simple VIE and look at the complexity of the answers. Then we will add the invariance and see if the answer becomes simpler. If in the end the answer becomes super simple, that means that we discovered the true physical factors of variations inside the system. Also very important thing is that the logic of how we use VIE in physics is in some sense orthogonal or opposite even how it is used in the computer science. So computer scientists try to make the VIEs representative. They want to have the latent space to express their data. In case of physics, we actually want the latent space to be as simple as possible, assuming that the VIE trained well. So we don't want to have a universal collapse of the representations, but if our latent distribution is simple, that we discover the true physics. I'll show you the example of how it works in the real world environment samples in a few minutes. Now, one of the things that you have noticed in this example with the cards is that the variation of the suit is ends up being one of the primary factors of variation in the data. It kind of makes sense. So can we deal with the examples when we know something about the data? And it turns out that we have several ways to structure our VIEs to be a little bit more complicated. So the first example is when the classes are known. So this becomes a conditional discrete condition variational autoencoder. So basically we encode each data set with the, each data with the class, and we decode it with the class. We create a own latent space for each class. So I've shown you the example of that for the MNIST dataset. The factors of variability can be known and continuous. So for example, you can take multiple images of the microstructure acquired at different imaging conditions or different temperatures or whatever, and you know what they are. In this case, there are two ways to work with this type of data. One is to use it as the ground truth label to see how the points evolve in the latent space. Another way to use it is to condition the latent space, to condition the data based on this variable. Then you will have their own latent space for each value of the condition, and you can interpolate between them, and to some very limited degree, you can extrapolate. So it can be super useful. We can have an examples when we have labels for some of the data points, but not all data points. So this becomes a semi-supervised VIE. So in this case, we provide the features and some labels. As an output, we have a disentangled data representation, and we also reconstruct the labels for each data. So that's very important because it allows us to give a large volumes of unlabeled data with a small number of labels and see what are the labels for the unlabeled data. So this, in some image recognition problems, that is a super powerful method. And then there are examples where the classes are known, the number of classes are known, but we don't know how they we don't know the label. So this becomes a joint VIE, which tries to essentially classify the data while disentangling the representation at the same time. So this is several ways how we can combine the partial knowledge of the labels, either continuous or discrete, with the VIE disentanglement of the variable. So which one we use depends on the specific problem. So the way it works is that we simply add the conditional loss. That's kind of all there is to that. So we class condition it. There are some tricks about how we can play with the reconstruction losses. So for example, if we make skip connection, we make the reconstruction much more robust. And these are the few examples of how it will work. So, for example, this is a conditional VAE, meaning that we create a latent space for each digit for the MNIST data set. And these are the examples when we do it for the VAE without rotation invariance. So this is a vanilla VAE. This is the VAE with the rotational invariance. So notice that if we don't have rotation invariance, then our reconstruction is, and obviously we use here the data set with the strong rotation. So we kind of rotated our MNIST images. So notice that in this case, the factor of variation becomes the angle, and the angle cannot be accommodated very well. So in the center of the latent representation, we see absolutely unphysical objects. So it's like a one that tries to be rotated in all directions at the same time. So eights become like a whatever point on the circle around it. Zeros can do that because zero can be rotation invariant, but 1 and 8 cannot. So this is actually a fundamental property of the VAE, is that ultimately what is the generative distribution in the VAE is apparently not that important. At least I have never seen cases where it made a difference, and I tried. But what matters is the topology of the VAE latent space. So for the normal VAE, it's isomorphic to the R2 space. For the rotation invariant VAE, it is isomorphic to the full rotation group space. And that part matters, and it's actually a very interesting connection between how VAE works and the topology of the data that you use to train it. Practically for rotation, the reconstruction is almost obvious, and now you can see that the factors of variation is essentially very subtle details of how people write zeros. For ones, there's kind of not much to show. All ones are the same. It's almost degenerate. For eights, it's also almost degenerate. So this is how the joint VAE works. So joint VAE basically tries to split the data and discover the continuous factor of variation and disentangle them, and the discrete factors of variation, meaning the classes. So practically, it is relatively difficult to convince it to train because it works well if the classes are balanced. If the classes are not balanced, that's something that we can control through the channel capacity type of terms. Unfortunately, in order to tune things based on the channel capacity, we actually need to know our classes. So that's become a little bit chicken and egg of the problem, chicken and egg problem. But practically, it works kind of well. Again, if we start with the MNIST data set, let's assume we take MNIST data set and we use the joint VAE and say that there are 6 classes. So we don't know what the classes are. We just say that there are 6 of them. So in this case, you can see that ones and zeros clearly become a class by itself. Sixes kind of become a class for itself, but fives and eights are mixed together. Threes and twos are mixed together. So if we say that there are 10 classes, so we know that MNIST has 10 independent classes. So let's tell the JVAE that there are 10 classes. It works better. So sixes, ones are clear, zero are clear, but you can still see that 5 and 8s are mixed, 5 and 2s are mixed, and so on and so forth. So essentially, we only were able to disentangle this new 4 and 9 classes and 7 classes. If we try to disentangle it in the 16 classes, again, it gets better. So now we have 6s and 9s more or less clear. But by now, you can see that zeros took 2 classes for itself. So apparently, there is a stronger variability between how people write zeros than how people write 9s and 4s. So it's a powerful tool, but it's not a silver bullet, and it requires quite a lot of hyperparameter tuning to make it work on the data with the known ground truth, which basically means that one has to be careful using it with the data when we don't have the known ground truth. And but the output would be the latent space for each class. So this is the transversal representation. So this is one latent direction, and this is a discrete latent direction. And this is the in-plane representation when we took two-dimensional continuous light and space for one discrete class. We didn't explore it. In too many detail, but one possible way forward to improve JVAE or get some idea about how they worked, whether they worked well or not, seems to be used through the ensemble. So imagine that if you have not one joint variational autoencoder, but you take 100 of them, and then you train them, and then you compare the results. So it turns out that the classes that are stable, meaning that they always form the same, are the classes corresponding to the pure ground truth. And when the autoencoder is not sure whether it's 6 or 5s, then it comes with the large changes. So we have a significant dispersion in prediction. So maybe this is the way how this type of algorithms can be harnessed in the future. Now, this being said, I've illustrated a few examples of joint VAs and joint VAs and conditional VAs. So how can they be used in the real world? So generally, most of my experience with these data sets stems from the work with the imaging and spectroscopy data in scanning probe and electron microscopy. Practically, they can be, with the same ease, can be applied to any data set from Raman, from nano-indentation, from any tool that generates the data. So imaging or spectroscopic data. So generally, our classical toolbox to work with this type of data sets are either linear dimensionality reduction methods, clustering methods, manifold learning, neural nets. So VAs are super useful for them. The problem is that if we want to use them for, let's say, image data, we need to find the right way to represent our data. I cannot just take a whole image from the microscope and send it directly into the variational autoencoders. And I cannot do it for two reasons. So reason number one is that one image is essentially one point in the data space. Secondly, one image is also a very high dimensional point. So practically what I need to do is to take my image and find some way to represent the much lower dimensional, but much more abundant and physically relevant descriptors out of that. In principle, this is how all neural networks, when we apply them to the image analysis, work. For example, the deep convolutional network start with this convolutional filters. So effectively, what they try to do is to represent the images, the kind of sliding window that splits it into the local neighborhoods, and then everything else is how the DCNNs operate. So if we try to analyze the real world data, it tends to be a better approach to build features based on the physics of the problem. For example, if we analyze atomically resolved data sets, we can find all the atoms through some form of segmentation, and then we can define each neighborhood through the radius vectors to the neighboring atoms. Or we can simply build a graph network, meaning the graph with the nodes being where the edges, where the atoms are, and edges being the bonds between them. So this works reasonably well. The disadvantage of this approach is that we drop a lot of information that is not associated with the atomic position. There is all types of useful image contrast around it. So, or the better way to engineer the features is to simply take some form of the wrapper points, for example, atoms or position of the grain boundaries or what's not, and simply create a patches centered on those features. So let me show you how the VAEs can be used to analyze this type of data set. So this is the data set of the electron microscope image formed between the lanthanum strontium manganite and nickel oxide. So you can clearly see this is perovskite, this is the rock salt. So the first thing is always find all the atoms. So this is our atom finding algorithm. You can see that we actually did a pretty good job of finding all the atoms here, and we did a pretty good job finding almost all atoms from this region. So that's kind of, I'm not going to go in details about how it is done. So for that type of things, it's either a log algorithm, which needs to be optimized, or the DCNNs. DCNNs take longer, but work better. Then what we can do is we can take these descriptors and put it in the autoencoder. And then, lo and behold, we start to get a very interesting representations of our data. For example, in this case, one of the latent variables look like this. So that's not a particular surprise, it's just separated two phases. But another latent representation is almost insensitive to the details of phase, but it shows some sort of variability in the image contrast that's clearly not related to phase itself. We can speculate that this is something related to the strain in the system. So we don't know. Latent variables are not particularly easy to interpret. So you need to dig deep into them in order to understand what they mean. But the fact that we took a relatively, that, by the way, notice that the image was rotated by 180 degrees. But notice that we took an image and then we were able to use an unsupervised learning. So we didn't have to put much effort in analyzing it. We don't introduce the human bias into the analysis, or at least introduce it in the way that is controllable. And immediately we start to see something that is absolutely not obvious on the original image. That's already worth a lot. So we can, of course, look at the evolution of what the latent variables mean by using the latent representation. So in this case, it's very clear that it represents the A lattice and B sublattice. We can play with the angle distributions in order to get a better idea of that. Or we can try to reproduce this analysis on the different image from the same series. And again, you can see that there is some factor of variability inside the nickel oxide layers. So definitely it tells us something interesting. Another super interesting thing that we noticed, and we are trying to operationalize and make it useful only at this point, is that in many cases, the instrument-related artifacts show only in one specific channel or one specific latent channel. So you can see that these lines, which are associated with the non-ideality of scanning in the electron microscope, they show up only in this latent channel, but they don't show up anywhere else. They're kind of sort of visible here, but clearly they are clearly separated in this image. So what else can we do? We can explore the latent distributions. So similar to the cards example, the latent distribution for images like this would be dominated by the types of atoms. So we simply separate the nickel oxide layers, the A side cations and B side cations. So the way that we do that is we take our latent distribution in the VA latent distribution, and then in addition to plotting the data, we also plot the kernel density estimates. So that's a kind of one small thing that matters, is that it's a kind of obvious thing that if you have a lot of data and you try to plot it as the distribution, we will see the outliers. But if we want to make a judgment where we see the points really are, we need to add the kernel density estimate, because if we don't do that, our judgment of the result would be totally different. What's very interesting is that if we look at the latent distribution here, you can see that these and these are strong, have a lot of mass density. So these are A and B sites. This is the nickel oxide phase. Notice that we have the intermediate kind of transitions from this one to this one, and from this one to this one, but we don't have anything on the line connecting those two. So this tells us what can happen in the system in terms of what are the crystallographically compatible, or at least representationally compatible, and what are incompatible areas. In other words, A side cation and B side cation look very different, and there is nothing in between. So this is the case where we actually, the reason why we come up with the joint variational autoencoders, they were created in order to deal with this type of situations. Now, another very interesting thing that happens with the autoencoders allow us to do is that they give almost impossibly uh, they give almost impossibly precise information about the uncontrollable factors of variation inside the material. So what I mean by that, that if I take the interesting looking images, meaning multiple phases, defects, whatever, VIEs are going to find those as the factors of variation. However, if I take the image of the ideal crystal, which doesn't show anything, any factors of variation visible by eye, and then I do the same analysis, then my VIE picture is going to identify the very small distortions that are associated with the imaging system. So for example, look at this image. This is a perfect single crystal, so you don't see much here. However, if I run the VA analysis, one of the latent variables has this broad band next to the left of the image. So we cannot really see it by eye. So this band actually appears because the electron microscopes have a flyback distortion. So if you scan on the one side of the image gets slightly distorted. And VA is powerful enough to actually reconstruct this distortion and visualize it. Again, we need to analyze this data to say what it is, but we actually can do that. So one of the ways to do that is, for example, take each unit cell, identify the strain almost by definition. So if we know coordinates of atoms and we know the ideal unit cell, we can reconstruct the strain term. And then we can basically make a linear regression and find out which combination of the strain terms gives us this latent variable. And we know that this latent variable is the non-ideality of the instrument. And if we develop this line of thought further, we can find ways to reconstruct, to do the correction for this type of distortion. And the correction, of course, is universal because it's connected to the way how our microscope works rather than to this specific sample. Now, I've shown you the examples of the VIE with atom finding. So we create a descriptor centered of atoms. So the natural question can be, can the variational autoencoders be useful if we don't want to find an atoms? After all, human eye can distinguish different phases of this image and this image, or different phases in this image and this image. Finding atoms is a very convenient procedure that's almost always worth doing if you analyze atomically resolved imaging data. The problem is that there are scenarios, first of all, depending on the signal to noise ratio, it can be difficult. And secondly, very often we work with images that don't have atomic features, but they have different type of regular patterns due to the domain structures and so on and so forth. So the question is, can we use VIEs to find the simplicity in those data sets? And the answer is yes, we can try. So this is what happens if we take this data, ferroelectric bismuth ferrite and the same two-phase mixture, and we try to apply the simple variational autoencoder on those. So notice what happens in this case. So we need to look at all three images. So this is our latent representation. This is our latent distribution with the superimposed kernel density estimate. So you need to look both on the blue dots and the red contours. This is our latent images. So latent images means that each point in image is colored by the latent value that came out of this location. So look what happens. For the simple VIE, we can see that our latent space clearly has this unphysical boundary. We can see that latent distribution is very, very complex. So there are two main groups, but there are these multiple kind of complex parts of the distribution. So generally, in my experience, complex distribution is the sign of the VIE analysis not working very well. So rather than finding several strong factors of variability, which represent the parsimony of the physical mechanism, we are finding a lot of mixed factors of variability, which means that it just doesn't work. And in this case, we can also see that from the Z1 and Z2. So our latent variables show like Moire pattern. So this is simply a beating between our sampling grid and the atomic grid, atomic lattice in the material. So we can identify it like a kind of twisted structure, whatever. For the second image, which is this one, it also didn't work particularly well. So the distributions are also fairly complex. The latent images show something, but the beating effects are there, and the latent representation is not super good. So how can we fix this problem? We can build the autoencoder, which uses the translational invariance. So once we add translational invariance, that simply represents the fact that our patch that we draw from the image can have any translation with respect to the atomic grid. So what we try to do is to compensate for the fact that where we don't know atoms are by giving the system a degree of freedom to shift itself across the image. And this is the example where it worked remarkably well. So look at our latent representation. It's perfect. Look at our atom latent distribution. So now we have only 3 main group of atoms, or 4 if you also count this one. And now look what our latent images are showing. So we started with the image that looks like this. So this is the substrate, but this is a ferroelectric material. Notice that the image is fairly dirty. There is all kind of extraneous contrast here, which kind of looks ugly. If we run the translational VIN on it, you can see that there are clearly seen regions with a different latent variable. So these regions are ferroelectric domains. And we got that without finding atoms. We simply used the translational invariant autoencoder, and it was able to separate the ferroelectric domains. And of course, it separated the substrate. And the latent distribution basically corresponds to one ferroelectric domain phase, another ferroelectric domain phase, and the substrate phase. So in this case, it's even simpler. We have a very simple latent distribution that have 2 peaks. One peak corresponds to one phase, another peak corresponds to another phase. And our second latent variable actually shows us something else. We don't know what this contrast is, but simply by the fact that this contrast appears on the length scales much larger than atomic scale, we know that it's something real. It represents some physical factor of variation inside the system. So this is the example of how you use this VIEs with the adding invariances in order to kind of unpeel the onion of the physical mechanism inside the system. So we use the simple VIE. It gave us the complex latent distributions and very unphysical latent images. So clearly we did not discover what the relative physics in this case. We took a slightly more complex VIE that separates the translation from other factors of variability. And lo and behold, our remaining factor of variabilities are physically relevant. So these are the ferroic variance and the kind of difference between ferroelectric and substrate. Our latent distributions are very well behaved, and everything else makes perfect sense. So once we get something like this, we can say that our VIE analysis of the data has been successful. So how does it work for more complex cases? So let's look at the example of the system with the chemical disorder. So this is graphene. So you can see carbon atoms. This is the contaminants, which have a lot of silicon atoms. This is the hole in graphene. So you can see the bright dots here. These are the silicon atoms inside the material. This, by the way, is brighter than silicon, so that's probably iron. The logic is again the same. We use the deep convolutional network in order to find all the atoms. So you see that all the carbons are found, all the silicons are found. The atoms that are brighter than silicon should be unignored, and the what's called the contaminants is also ignored. So we focused our analysis only on the objects that we are interested in. So this is how the VIE is going to look at this data set. So we get the angles image. So angle just shows the different two possible orientation of sp2 bound carbon. These are the latent variables. So notice that once you look at this image, the meaning of the latent variable becomes immediately obvious, because if the carbon is ideal, so it's ideal hexagonal lattice, the latent variable is close to 1. If we have disorder, then the latent variable is very different from 1. So it's kind of way how we can identify them. So this is a kind of example of how the VA trains. So look at this part. So you can see that first it learned to recognize the patterns in one direction, and then it locked in and started to recognize the structures of the local neighborhood. And this is kind of the dynamic image when we use the video of the graphene evolving in the microscope. And we color it by the latent variable. So you see that we can now visualize the dynamics of these rafts of the ideal graphene and the behavior of the disorder, which kind of evolves under the action of the electron beam. So if you're interested in the physics of graphene and the chemistry of graphene, it's all now visualized with the single atom distribution. What's even more interesting and kind of additional degree of freedom in the VAE analysis is that for complex system, we can balance the reconstruction quality versus the Kullback-Leibniz term. And we can change the structure of the VAE by adding skip connections, similar as in UNets. And we can also add the put an emphasis on the reconstruction rather than anything else. So what happens in this case is actually super interesting, that this is the example of the latent space of variational autoencoder trained on this image of set of images from the evolving graphene. So this part of the latent space is populated by very simple, essentially three hexagonal rings, which is what we believe is the main building block of the graphene. This part of the latent space is populated by considerably more complex objects. So for example, here you can see the 7-member ring next to the 6-member ring. Here you can see clearly 6-member ring close to the edge. Here you can see the 6-member ring, 5-member ring, and kind of 7-member ring. So this looks very plausible. And that kind of reminds us of the how the carbon atoms can arrange from the standard chemistry textbook. But notice one very important thing, that whenever we work with the machine learning algorithms, we always tend to make this mistake of interpreting the results of the ML algorithm in terms of what humans already know. And the natural way to look at this data is say that, hey, we all know that the carbon can form rings. It's natural that we see them on this set of images. That's not entirely a correct viewpoint, because we as humans know how the carbon atoms can arrange themselves. But the machine learning algorithm that we used is not human and has not read the Ternay textbook, so it doesn't know how the carbon atoms work. So what happened in this case, we start from the pure physical observations. So that's the data coming from our microscope, and it represents the evolution of the microstructure. We use the deep convolutional network to find all the atoms. So this is a supervised step. So we rely on the fact that atoms exist, they're discrete and have a known shape, and human can recognize them. Atoms can be found in many other ways, and of course we can find the features of interest using any other algorithm. Like I can use Kanye filter to find edges, I can use whatever half transform to find other type of object, it doesn't matter. But once I discovered those objects and I sent it to the VAE, this is unsupervised learning method. All this method knows, or all the only new knowledge that I incorporate in the analysis, is that I'm saying that structures are parsimonious in nature. There are very few of them. And only with this postulate, the variational autoencoder start to uncover the structures that come like they came from the pages of the organic chemistry textbook. But they are not coming from organic chemistry textbook. They are discovered from the data in the unsupervised manner. And the reason that I understand what it is because it resonates with what I know about organic chemistry. So it is not an obvious result. It's actually the result where the machine learning algorithm made a discovery, and the human made this discovery and made it explainable. So that brings a very interesting question of whether we can discover new things from the machine learning analysis of the experimental data. So about 2 years ago, I would kind of make a joke that maybe not really, because if we cannot discover the new physics from machine learning analysis of the experimental data, because if we understand what we got, it is not new, and if we don't understand, then it's not physics. That's not exactly true. There is a very narrow range of opportunities where we actually can discover new physics, but it's very domain specific. So we can learn one step ahead of what we know, but maybe not 10 steps ahead of what we know. So another interesting thing, so going to the point of the how does the disentanglement of the representation look like in this case? So in this case, our latent space encodes the structures. So we can enumerate each structure by the number of the rings of 5, 6, and 7 members adjacent to the central atom. So as you can see, there is a very interesting distribution of this in the latent space. For example, this part is the ideal graphene. We have 3 6-member rings, and we have 0, 5, and 7. This is the part where we sort of have the edges when we have 2 6-member rings, and then we can have either 2 edges when there is 6 and 7, or 6 and 5, and so on and so forth. But anyway, this is how the disentanglement of representation look like in this case. And you can see that this latent space is absolutely not random. It's complex, but it's not random at all. It represents the way that the graphene can be organized. And again, this is learned in an unsupervised manner. So what about other examples? So atomically resolved structures are great, but you can always say that, come on, it's a very small subset of the real world. You're right, but that's the beauty of the variational autoencoder, is that we can use them for any complex data set, whether it is image, video, atomically resolved, not atomically resolved, spectroscopy, and so on. So this is an example of the ferroelectric switching visualized by scanning probe microscope. So you basically see how the domains evolve inside this material. So if you look at it, you can see how the 180-degree walls move, how the ferroelastic walls reorganize, and so on and so forth. How can we use the autoencoder for those? Well, the first step is to find the domain walls. It's usually a much better start than just using the rectangular grid sampling. Finding 180-degree domain walls is straightforward. They can be found just by Canny filter and give a very good image. Finding the non-180-degree domain walls is more complicated, so that required building the REST headnet type of architecture, but that can also be done. And once we do that, we can take this data set and put it in the autoencoder. And the way that we choose the descriptors is basically the squares centered at the domain walls. And now you can see that our latent space encodes the possible domain structures inside the material. So this is the region of well-defined 180-degree domain walls. This region is occupied by the needles of the domain. And these are the regions that are occupied by more complex domain structures. So, and then we can sort of see how the physical parameters change across this latent space. For example, this is our degree of switching, which is simply the ratio of the dark to bright regions. You can see that it is really relatively well distributed across the domain space. This is our average wall curvature. So this is the domain count. So again, these parameters, so these are human interpretable quantities. But interestingly enough, these human interpreted quantities have complex but relatively smooth and organized representations across the latent space. We can run more complex examples when we can create the descriptors when it is centered at domain wall observed at time t, but the patch is taken at the domain of the time t plus delta t. So then it encodes the time variation. So in this case, latent space become more complicated. So when it looks like this, I'm very tempted to say that we don't have enough data, and they start to show fairly complex structures in it. But nonetheless, we can get some idea about the properties of the domain. And we also can enumerate how the how the wall parameters change during the dynamic. So if the domain wall moves, we can essentially encode the evolution of the latent variables across this domain wall. And what we see is, again, absolutely not random. So you can see that there are some interesting similarity across the domain wall motion. We don't know what it means because um, this is the case where we looked at available data, start to come to conclusion that maybe we are close to the overfitting, meaning that there is not enough data. But the important thing is that we see something happening, and we can even connect it to the obvious trend. Like you can see that here in the region with the bright contrast, the domain wall is clearly pinned much stronger. If you see the wall motion, you can see that here it sort of lags behind the rest of the wall. At the same time, in these dark regions, the wall kind of tries to go ahead. So we do learn something about the wall dynamics. And the final thing is that can we get insight in physics? And this is the example where decoding the information learned from the variational autoencoder took maybe 2-3 weeks, but it was a lot of fun. So look at this data set. So in this case, it is the same image. This is the 180-degree domain walls. This is the 180-degree domain walls and non-180-degree domain walls shown separately. So blue are 180 and the red are not 180. And this is a local kind of zoom in from one image. So this is a single snapshot. Practically, we have a video of this process, so it's kind of much more data than this. Now, in this case, we can create autoencoder which uses the 180-degree domain walls as one channel and non-180-degree domain walls as a different channel. So we're trying to learn the joint behavior of 180 and non-180-degree domain walls. And then when we formed the latent representation like this, we thought that, okay, what does it even mean? It's absolutely not obvious. But it turns out that if you spend a little bit of time and sort of think about the physics of the system that you study, this type of things are actually relatively straightforward to understand. So in this part of the latent space, you can see that 180-degree domain walls and non-180-degree domain walls are co-aligned and have equal intensity. That basically means that here these walls are pinned on each other, so they coincide. What happens in this part, you can see that the red line is visible, but the blue line is kind of more diffuse. What it means is that we are in this type of regions where the domain wall, the red domain wall, is pinned on multiple blue domain walls, but we don't have enough representation power in order to resolve where they are. And this is the most interesting part. So you see here that in this part of the latent space, the red lines are much weaker, and they have this funny contrast when they are very strong in the center where we took our patch. But the intensity of the red contrast decays close to the edge of the patches. So here, this is not happening. They have equal intensity across the whole line. Here is strong in the center, weaker to the edge. So what it means is that this domain wall is not pinned, which basically means that we can choose the center, but the edges kind of move in any which direction, and therefore they average to much lower value. So after a while, if we look at something like this, it's a little bit abstract representation, but once you think about it, then it maps exactly on the physical mechanism that we are interested in, and we can visualize them, quantify them, and kind of make sense about what they mean. So it's not going to be unambiguous, but it illustrates that we can decode complex mechanism through the VIE space rather than anything else. The reason why we want to do it through the VIE space rather than through the observation of the individual elements, like you can say, okay, I observe this movie, I can observe all those mechanisms individually. I can focus my attention here and see how the domain wall pins on the 180-degree domain walls. I can choose my attention here and see how the ferroelastic domains are evolving. There is two problems that human attention would be limited to the point assessment. We can always find the mechanism that comports to our expectations. We, however, are not ideal, and we will miss the mechanism that don't comport to our expectation. So the VAE and any machine learning approach is more difficult to interpret, but it gives the mechanism when they represent the whole of our observation in the unbiased form. So that's a top-down view, not the fixing your attention on the individual small detail. So practically, we of course need both, but this is a very second way of doing that. So now let me briefly show a few more examples of how we can use the VAEs. And here the key thing is that nobody told us that it has to be autoencoder. So in principle, we have multiple experimental scenarios where we can measure pairs of variables. For example, we measure local structure and we measure the local spectrum. So it can be a Pierce response microscopy where the image is domains and spectra hysteresis loop. It can be STEM ILS where we measure the local structure in STEM and take the local spectroscopy in ILS. It can be nanoindentation where we measure the local structure visible in the SEMO optics and we measure the local indentation curve. So it can be, I mean, the same type of approach obviously applies to the molecular structures where we can input the molecular structure and the output can be adsorption spectra. So there are multiple examples when we have the pairs of the disparate information. So it is very natural to extend the VA approach to the encoder decoder, where we start with where we encode one type of data, and then we take this encoded Latin vector and then decode it into the paired output. So for example, this is the example of the input domain structure, output the hysteresis loop. So if we train the network like this, we essentially learn a correlative relationship between the local structures and local spectroscopies. So the way that we examine the structures is through the same Latin spaces, so there is nothing unusual here. Interestingly enough, this approach works remarkably well. So for example, this is the prediction where our input is the domain structures and the outputs are the spectra. So obviously this is a test example. This is not the training data set. And you can see that the prediction and the ground truth actually match reasonably close. And this is another example where, I mean, it's not perfect, but good enough. So this works for scanning probe microscopy. This works for ILS data sets. So in fact, we can kind of make it work both directions. So we can take the image and predict the ILS spectrum to it. And then we can take the spectrum and try to find out what would be the image. So we can train on those as features and spectra as targets, or we can train on spectra as features and the images as targets. So here it's kind of interesting that prediction of spectrum from image works remarkably well. So you can see that the ground truth and prediction are very, very close. The prediction of image from spectrum doesn't work very well. So this is the prediction, this is ground truth. You can see that they are not they're not identical, but the main features are the same. So here you have a corner missing, here you have a corner missing by a different coordination. So here you have an edge, here you have an edge. So this one didn't work very well, but again, so it's surprising that you can reconstruct the image from spectrum in the first place. So it turns out that the problem of the encoder decoder is that it treats the image and spectra differently. So if we have this approach, we kind of can, we essentially have to do two encoder decoders. One is the image to spectrum and another is spectrum to image. So this is not super convenient because it's difficult to backpropagate from one to another. But the way to do it better is to come up with the dual VA approach, where what we do is we still take our pairs of data. So for example, the structure and spectrum, Then we have two encoders that encode them into the common Latin space. And then we have two decoders that decode them from the common Latin space. Within the Latin space, there are several ways how we can impose the similarity between the Latin distributions. So we can say that this is rigid, meaning that the Latin code for both of those should be identical. We can say that we want to also add the second term that minimizes cosine similarity between those, so tries to make them close, but tries to do it in the kind of soft way. So there are several strategies for doing that. But once we've done it, the results can be super interesting. So imagine that we have our data sets. This is the SEM data, which is structural information. This is the hyperspectral optical imaging. So these are far field optical spectra. So if we use this approach, this is what is going to happen. So this is our Latin spaces. So we have clearly disentangled the representation of the data. So the monomers are here, clusters are sitting here. We disentangle the representations of the spectra. And then we can solve this problem of identification of structure from spectrum. So imagine that this is our far field optical image. So the nice thing is that this is a cheap measurement. We can take a camera, we can take these particles, and we can take any amount of the optical data sets over like literally tens of thousands of particles. Just how long are you willing to take the measurements and where are you going to store the data. So zooming in on each of those regions and taking SEM images considerably more time consuming. It's doable, but you have to do it one by one. But notice how well we can reconstruct the particle shape based on the optical spectra. So these are ground truths. These are prediction based on optical spectra. The whole dual VIE is trained based on the 300 examples. So the way things are going in the ML world, it's not a lot. 300 is kind of being very, very considerate. The trick is we also build it with the rotational invariance, so it kind of doesn't care about the orientation of the cluster, and without rotational invariance, it will just not work completely. But look what happens. So this is ground truth, this is prediction. So of course, we were not able to reconstruct the subtle detail that this is octahedral and this is, I don't remember what the name of this is, but kind of whatever, they look more like spheres, but this is clearly a trimer. This one reconstructed by this one, also trimer. We were okay reconstructing the tetramer. So the single ones are reconstructed super well. If we have the 5 particles, well, it didn't reconstruct particularly well, so that's clearly not a good one, but come on. This dimer, for whatever reason, was reconstructed by trimer, but we see that there is a strong distortion around it, so that's indicated that things didn't work well. This dimer got reconstructed as the dimer with a different orientation, but again, we have a rotational invariant case. So in other words, it actually works remarkably well, and this dual VI is the way to build the structure property relationships.
Can I ask you a question, Sergey?
Sure.
Again, I'm not an expert in this field, so correct me if I'm wrong. How many structures can we make with 4 elements? Is it only 1 or 2 or more? Particularly, I'm asking this question to see if you tested actually to see if this method can distinguish between different structures with the same number of elements. Because when I looked at the left image, the first thing that occurred to me was that, okay, you can sort of count the number of elements using maybe the intensity. Maybe that's what the ML did. So basically to test this hypothesis, I was thinking that are there like more structures that we can test using same number of molecules or elements?
That's a good guess. So in fact, we run the analysis when the curves are normalized and not normalized. So we did it in both cases. If I remember correctly, this is the reconstruction when the spectra already normalized on intensity from 0 to 1. So we in this case, we look at the structure of the spectrum. So how many peaks it has. So notice that this is how the Latin space look like. So these are kind of can be taken as a pair. So if we have ones, they have they will look like this. If we have multiple, the peaks are shifted. And there is a second peaks on the right, and so on and so forth.
Thank you.
Mm-hmm. So, in some sense, in this case, kind of connecting, how is it all connected to the Bayesian optimization and the deep kernel learning? So the way it is connected to the Bayesian optimization and the deep kernel learning is that in this case, we had all the pairs of data from the very beginning. So we first took the data, and then we analyzed it using the dual variational autoencoder. So in many cases, we in the experimentally have a slightly different problem of, for example, having access to all the structures and then choosing where to take the spectral data. So for example, if we take the SPM or STEM or optical image, we need to choose the location to do the non-indentation, to do the spectral measurement. There can be inverse problem. For example, we can take a lot of hyperspectral data, and then we need to have some way to choose where to do the high resolution SEM measurements. So there are two ways of doing that. One way is to analyze the variability of known data and come up with the sampling strategy based on this variability. So this is essentially a sampling from the latent space of the autoencoder. So we want to represent all variables, factors of variability equally. That's one way of doing it. Second way of doing it is to rely on the human interest. So I can simply say that I like these images and I like these structures and I don't like these structures, and kind of introduce the human preference into analysis. But the third way becomes that imagine that this is easy to measure and this is difficult to measure. So imagine that I want to guide our exploration in such a way that I learn how to identify the pentamers without knowing where they are on this image. So the deep kernel learning is an example of the machine learning strategy that allows you to navigate complex multidimensional search spaces in such a way to find the useful functionality. So in some sense, deep kernel learning is the type of machine learning algorithm that does something that humans, in fact, cannot do. So most of the time, we're using machine learning in order to simplify the data, in order to find some internal trends, or to solve human-level tasks. So once we use supervised neural networks, they do the things that humans can do, and very often not nearly as good. So we always benchmark neural networks to the human level, and we never get 100%. There are caveats to this statement, but roughly we don't expect them to do much better than human. We expect them to do faster than human and at much lower cost. But the deep kernel learning, which is the automated version of this type of analysis, does things that human cannot do, and we'll talk about it later. So now with this, we got some basic introduction into the VAEs. So if you're interested, my group has put a very detailed summary of how they can look like and associate GitHub repository that you can get access to. So that's publicly available. Now let's look at one example of how we can combine VAEs and the Bayesian optimization. So here we have two key elements. One element is that the VAE is very good in taking the complex data sets and build a low-dimensional representation of this data set. Bayesian optimization is good in exploring relatively low-dimensional search spaces in order to, yeah, I'll do that. Very good in exploring the relatively low-dimensional spaces in search of interesting functionalities. So, and the third thing is that we know that when VAE form the latent spaces, they decouple the factors of variation inside this latent spaces. So we have seen multiple examples, which basically means that the latent space of the variational autoencoder would be well behaved, at least locally, with respect to the factor of variations in the data. So the next step of imagination we can make is that if the latent space is locally smooth with respect to factor variation, then it would be the property that we're interested in would be reasonably well behaved over this latent space, which basically means that exploring these latent spaces towards the useful functionality gives us this trail of the breadcrumbs that can bring us from the initial seed points where we start exploration to the points where these useful functionalities are maximized. That's a very, very important thing, and success of the areas ranging from natural language programming to molecular discovery to type of things that we are going to talk now, like process optimization, basically hinges on what are the property of the latent space. So how smooth and differentiable it is, and how well are the property of the latent space correlated with our end target. So let me start today showing how it works for the VIE BO combination. And on Wednesday, we will continue that for the deep kernel learning. And I guess I'm not going to reveal any particular secret saying that the DKL will work much better. But first, let me introduce the problem. And at some point, the difficulty in this type of scenarios become that you need to come up with a toy model which is sufficiently complex to be, which is kind of simple, but as simple as possible, but sufficiently complex to represent the physics and the interesting properties. So for us, such model was what we call a Ferrocene model. So basically, all you need to know about it is that this is a hybrid between the Ising model and Ginzburg-Landau model. So it's Ising model in the sense that we have the spins defined on the lattice. It's a Ginzburg-Landau model in the sense that each of the spins follows the Ginzburg-Landau equation rather than the normal flip up and down in the Ising model. So the reason why we adopted this model, so it was proposed by the gentleman whose name I forgot in around 2000. The reason why we adopted it is because this model is ideally matched to the nature of observations in the electron microscope. So in the electron microscope, we see the individual atomic columns. So the polarization in plane is a discrete, kind of is defined on the discrete positions, but along the z direction, it's average along the beam path. So we felt that it is the right way to match complexity of physics and the observational model. So that's all you need to know about it. The important thing is that this model allows us to model things like a hysteresis. So we can introduce the noise in the system. We can apply the external electric field. So this is how the electric field is changed. And this is how the total polarization changes, the red curve. And the green curve here is the curl of polarization. So curl is interesting because according to symmetry, curl in this system should be 0. But practically, because there are defects, they result in symmetry breaking, and the curl can become not 0. So we asked ourselves a question, can we somehow create a history of the electric field that will actually maximize this curl? You can see that this is kind of a little bit non-stationary. It kind of changes from one cycle to another. So can we find the maximum of the curl? So how can we do that? So what we wanted to do is to cast it first as the Bayesian optimization problem. So what we do is that we start with some set of possible trajectories. We encode them in the latent space of the autoencoder, and then we try to do the Bayesian optimization in this latent space. So the key thing here is that if we do something like this, we need to come up with the family of the trajectories that we want to encode. Because obviously the most general case, this is kind of can be any function or Gaussian process or whatever. That's a legitimate way of doing that. But practically what we can do is to create a family of the curves corresponding based on sort of domain experience. So we can have the sine waves that decrease in decrement, so either slowly or faster or very fast. We can come up with the families of the sine waves that open up, so either reasonably slowly or very rapidly. And then we say that these are the type of curves that allow us to make the system represent sufficient variability to explore the behavior of the systems. So then what we do is we take these curves, and then we kind of can look at the distribution of those in the latent variable in the system. So what you see here is our familiar latent representation. So these are how the parameters are distributed in the latent space. So this is what the parameters are. So it's amplitude, the essentially the decrement, increasing or decreasing. This is the frequency. So you can see that, for example, this is how frequencies are distributed in the latent space. You can see this is how the decrements distributed in the latent space. So we see the same, we see that the latent space of the autoencoder trained on the variables preserves and disentangles the factors of variability in the trajectories. And then what we did was, so whenever you can, it's always a good idea to calculate the ground truth behavior. So it's a little bit defeats the purpose of the active learning, but it's very good in order to understand in which cases latent active learning works or not. So see what we have done here. So we have our latent space of the system. Latent space, by definition, is a generative space. So we train it on the certain number of trajectories that gives us latent distribution, but we can decode the trajectory from any point of the latent space, including those that was a part of the original training set and those that were not a part of the original training set. And that's what we can do is that we can decode the trajectory from some part of this latent space. We can give this trajectory to our model. So rather than having the electric field which is sinusoidal, we are going to have the whatever trajectory we decoded from the latent space. And then we are going to take the curl at the end of this process, so whatever value ends up being at the last time point. And we are going to plot this curl as the function of these latent variables. So rather than having a collection of the curves that we trained our autoencoder on, we use it as a generative model. So we trained it, then we take a point from the latent space, we send it as the input to the model, we look at the curl and the end of it. And what you see here is the examples of the several curves. So for example, this one, so the red curve is always the curl versus time. The blue curve is the evolution of the electric field. So if we are in this part of the latent space, so the point 1, this is the red one is our field. So this is kind of rapid jump and then stabilizes. The blue is the evolution of the curl. So this is where we stopped. Nothing changed after this point. So as you can see that in the end, the curl is fairly small. So this is the point number 2. So in this case, you can see that our field goes like this. So it's kind of increasing sine wave. And you can see that this is the evolution of the curl. So this is where we stopped. Here, the curl is relatively fast, relatively large. And then each of those curves kind of come from a certain region of the latent space. So if it comes with a certain region of the latent space, that means that we can reconstruct the trajectory that corresponds to this point. And after the simulation, we get the curl. So see how the distribution of this maximum curl in the latent space look like. So first of all, it's definitely ordered. You can see that the large curl is localized in this complex manifold. It's not everywhere. It's kind of has a structure. Secondly, notice that, I mean, that's the reason why I like to show this example, because at the same time, it's sufficiently easy, sufficiently simple, but at the same time, it shows the super interesting behaviors. So notice that we don't have a single maximum in this case. We, in fact, have the very complex manifolds, not very complex, sufficiently complex manifolds on which the maximum sits. And also notice that these manifolds are kind of separated by the dips on which the curl is low. So what does it mean? It means that if we try to find it using the gradient descent in the latent space, we can start from this point, and using the gradient descent, we can probably get somewhere here. Maybe we will be able to get around it, maybe not. If we start here, gradient descent is never going to bring us here or here. It's just get stuck on these features. That being said, if we use the, so this is kind of the Bayesian optimization, it will work better. So we, of course, can use the same type of data to explore other properties, so not only curl, but also the total polarization, normalized curve, and so on and so forth. So the important thing to notice is that once we plot multiple parameters in the latent space, we can see how they're related. So one thing that you will notice is that the curl is maximum here, and this roughly, but not exactly, corresponds to the regions where the magnetization is zero. So in other words, that kind of suggests us that the curl becomes large when the average magnetization of the system is fairly low, which means that the spins have flexibility in order to form the curly structures, rather all be arranged in the same direction. But that's a correlation. It's not. It's close enough, but it's not identical. So we can explore those in more detail, and in the end, we can also run the Bayesian optimization on this type of approach. So notice the very important thing that, first of all, we have to start with 100 initial points. That's a lot. We run the exploration for 600 steps. So notice how our space is explored. So first of all, we did find our maxima, which is good. So here you can see the original curl service. So that basically is the ground truth data and the Bayesian exploration on top of it. This is the reconstructed curl surface. So this is how the Gaussian process thinks the curl is distributed. So you can see that the reconstructed and the original are fairly close. But notice a very, very important thing, that in this case, the features on which the interesting behaviors are localized, they are kind of localized, but they're not. It's not like a simple maximum. It's a fairly complex manifold. And remember the primary principle, the primary consideration about the simple Gaussian process, that we have a single kernel. The length scale of the kernel represents the length scale at which the properties change. So the Bayesian optimization doesn't trust the properties if they're further away than the kernel length. As you can see on the ground truth data, the size of these features is relatively small, and they also have kind of any which orientation in the latent space, which basically means that the kernel length is actually also very small. If the kernel length here is small, that means that the algorithm have to explore the all latent space in such a way that the distance between the sample points does not exceed the kernel length scale, which in turn is related to the scale of these features. And even though, notice that finer elements are not very well reconstructed. So you can see that here there is a region where the curl is clearly sharp, but the width of this ridge is very, very small. And it's not discovered. We don't have a single point coming from here. So what are the good news and what are the bad news? So the good news is that it is possible to use Bayesian optimization over the latent space of the system. We can use the variational autoencoders of some sort in order to go from large dimensional system and make it low dimensional system. We can use it to encode the training trajectory. So if you want to charge batteries, we can use this for battery charging trajectories. If you want to discover properties of molecular structures, we can do it with the molecular structures. And that was the Gomez-Bombarelli paper in 2018. If you want to build structure property relationship for complex microstructures, you can do it as well. You can encode the microstructure in the latent space and then explore the properties in this latent space, and it will work. it will work because we always postulate that there is a relationship between structure and properties. Otherwise, we cannot study structure-property relationship. And because the variational autoencoder will make the representations where the representations of the data are disentangled, and therefore locally they well behaved. But as you can see in this example, and as you have seen in the example of the cars data sets before, the geometry of this manifold on which good properties are localized can be fairly complicated. And once, for example, it can be very, very thin. And once it is the case, the representation, the Bayesian optimization gives us gain. So it's much better to study it using the 600 points as opposed to the ground truth, which was like 10,000 or something like this. There is a gain, but this gain is not super large. This gain is determined by how well is the latent space structured, and with the simple VIEs, we don't have control of that. And it's also determined by the relationship between the structure and properties. If there is a certain type of structures that give rise to certain properties and it is only one, VIE-BO will work like a charm. If there are several classes of structures, each of those give rise to the properties, then the maximum of properties can have very complex distributions determined by what is the difference of structures and how the VIE tries to kind of squeeze them into one latent space. So this type of approaches work very well, but it can work better. And on Wednesday, I'm going to show how we can run the deep kernel learning. So deep kernel learning is a supervised method where all features are available at the same time, but targets are becoming available sequentially. So it combines, in some sense, the VIE approach and the Gaussian process approach. It's just that they're trained together. And that gives absolutely wonderful results if you try to apply it to those type of problems. So this being said, this is it for today. So Greg has posted the archive, the repository for the VIEs. So that one would be that one would have a tremendous amount of the information about the autoencoders. But let me put the one that I was referring to. Where is it? Give me 1 second. And so now is the good time for questions. Okay, so this is the archive and the detailed tutorials on all kind of VIEs. You can find them here. So these are very large collection of the. This is a very large collection of the tutorial notebooks on the different VIE types. So in principle, it may take kind of several days to go through them and follow the logic, but they're all fully functional and potentially super useful. So any questions?
Yeah, I have a quick question. So can you hear me?
Sure, yep.
Yeah. So from all this discussion, it seems that all revolves on how we can put together a meaningful latent space for our problem, right? So
Yep.
since you're working with images, it makes sense to have latent space to the reduced size of your image, but in 3 channels if your image is RGB. But how is there like a rule of thumb or like a good strategy for defining your latent spacing? And in a way that's meaningful for your experiment?
So look at it this way. So when we want to make an optimization or discovery in the high dimensional spaces, there is no one single way of doing it, right? So for example, if we want to discover something in the high dimensional space, like find something interesting in the spectrum or image, or find the process trajectory that gives us the best result when we use it to optimize the material. Roughly speaking, it is all the same problem of either discovery in the high dimensional spaces or active learning in the high dimensional spaces. It is discovery when we have a lot of objects, like multiple spectra, whatever. It is active learning when we don't have structure, when we have to kind of explore it one by one. So the best way for dealing with this type of problems are the cases when we have the reliable physical model. So the thing that I generally teach to all my students in any class that I teach about machine learning, that we use machine learning if and only if we don't have a good physical model. If we have a physical model that we believe in, that fully describes our data, whatever, we shouldn't even start doing machine learning. It's a wrong way to go. Whenever we pick the machine learning model, we always try to pick one that is fully consistent with the image. So PCA is great if we don't know anything about our data. Bayesian linear unmixing is good once there is a kind of like chemometric sum plus one. Autoencoders are good when we know that the factors of variation in the data are nonlinear. I have several examples of the systems. Like if I want to use so for example, I will not use variational autoencoder for the hyperspectral optical imaging data. And I will generally be very careful using them for cathodoluminescence data, because these imaging methods are linear in nature. So the signal is the linear combination of the source signals. And if we know that they are linear, we should use the linear unmixing. Using nonlinear methods like VIE will introduce, it's kind of essentially overfits in the sense of making the image formation mechanism more complex than it really is. So the second best step is when we know the human heuristics that tells us how to engineer the features correctly. So notice that if you take any standard machine learning course, it basically tells you that for any realistic business problem, the key problem is always feature engineering. So if we have a complex data, sometimes we know that this part is important, this part is less important. We can engineer features that represent what we're interested in. We can do it by, if we take a spectrum, we can do the linear fit, the least square fit and reduce it to the position, widths, and the amplitudes of the peaks. So the large dimensional data set is becoming a small dimensional data set. If this representation as the fitting function fully represents the data, so the errors are small, then we reduced our dimensionality of the data through physics rather than machine learning. We use the VAEs if and only if these strategies don't work or if we want to experiment. So sometimes we can run multiple strategies and then use the weak learner approach, seeing how the results of analysis by the range of models evolve. So VAEs is the ideal approach when we don't understand the physics very well, when the data is noisy, meaning that the uncertainty of the physical fit would be large, and then they work remarkably well. So then we can use them. We have some degree of interpretability of the latent space, and the way we do it is basically look at the latent space and try to analyze the curves from the latent, the decoded curve from the latent space, like we would analyze the experimental data. And then we see how this analysis propagates for the rest of the latent space. And, it's kind of very iterative process.
Okay, thank you.
My pleasure. So any more questions?
Can I ask a quick question?
Sure.
So It's sort of like an ask for advice. So let's say you have some sort of signal. It could be spectroscopy measurement or something. And then let's say you don't have a physical model, but you have a like mechanistic model, semi-mechanistic. So parameters of this model are not entirely physical, but it's not also like just a polynomial fit. So it's sort of a pseudo-mechanistic model. Do you think is it a better approach to directly map that signal to the quantity that we're interested in, or do it through this intermediate layer? So first do that pseudo physics-based model ourselves, and then use that filtered data, which sort of reduces the dimensionality of that input signal, and then do another maybe autoencoder or some other model to get the metric we want.
So again, there are multiple ways to approach it. It depends what you know about the physics. So at least for the time being, if you know the physics partially, the best approaches are based on things like physics-informed neural networks or the neural operators, which allow you to encode the physics as the part of your denoising process, or super resolution process. So this works absolutely fantastic. With a normal data-driven process, things like variational autoencoder, there would be a very real risk that some features of the training set would be superimposed on the deconvoluted data. So as I said, if I train the autoencoder on the data that has a specific fit, and then a specific peak, and then I apply this autoencoder to denoise the data that has noise but not this peak, then the noise would be interpreted as a peak.
I see.
So that is a very easy way to contaminate your analysis by the features in the training data. And that's a very big limiting factor in using variational autoencoders universally. So there is no such thing as free super resolution. So super resolution or the information recovery always kind of uses something, either training data or the physics of the system or whatever. And you need to kind of very carefully keep track of what is that you give to the system, so it produces the quote unquote information that was not a part of the original data. So there is nothing wrong with this type of approaches. It's just that one has to be very paranoid with interpreting them.
I see. Thank you.
My pleasure. Okay, so let's call it a day then, and call it a day, and talk with you on Wednesday.